right, we're recording. Welcome everyone to week 4, day 2 of CSI 45. And yeah, Mr. Robot is reasonably technically accurate, which is not a award I give to many TV shows. Yeah, they even casually mention a Raspberry Pi in it. You know, apparently Raspberry Pis are for hacking, but I know what a Raspberry Pi is. Like, yeah, they're a $35 computer, dude. They're not for hacking, but you know, they sneak a Raspberry Pi into like a data center and use it to infiltrate it from the inside. So, you know, it's not terrible. It's not terrible. Most TV shows just have this really garbage technobabble. I constructed an IEP using the hyperlink protocol, and you're like, no, that's not how any of this works. Agents of S.H.I.E.L.D., you know. So, yeah, I didn't watch anything past the first season, but yeah, I enjoyed it. All right, so there are some questions about the homework assignment, and if we, I'll just pull that over here real fast and answer them. So DeBello says, I'm not even sure I'm reading the text screen in my perm correctly or even at all. So when you are given a, when your function is called, the first parameter to the function is passed in R0, usually. If you have 64-bit parameters, it's passed in R0 and R1. But we haven't done 64-bit numbers yet, so don't worry about it. Yeah, so the first parameter is going to be passed in R0, the second parameter is going to be passed in R1, third parameter is passed in R2, fourth parameter is passed in R3. Anything after that is passed in on the stack. And the return value, there's only one return value in C, right? The return value is passed in R0. So if you do this code here, move R4 0, move R6 0, R4 holds 0, R6 holds 0, and this will load into R5 from memory address 0 plus 0, which is 0. So you're loading from memory address 0. So this is, you know, this classic video.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
Right. So Brett the Hitman Hart, obviously one of the world's best computer programmers, the greatest that is, that was, and ever will be. Found the bug in your code. If you try loading from memory address 0, it will crash your code. Unix does not allow you to read from memory address 0 or anywhere near it, because people make this mistake all the time. And so if you try loading a byte of memory from memory address 0, it will be outside of the segment of your program. The operating system will detect you're reading something from outside of the segment of your program, and it will kill your program. Okay. So Singh says R0 is the input string as R, R4 could be the index, R5 could be where you're storing. Yeah, so it's going to write from R0 plus R4 into R5. I would not read from R0 though, because R0 is used both as the parameter to your program and the return value. So if the first time you call a function, it's going to overwrite R0. So think of R0 through R3 as being temporary variables, and don't leave anything in there that you don't want to have overridden the first time you do a function call. So what I would do is, like in my program, which it took me 20 minutes to actually write the homework last night. So it's not a long program, but it also goes a lot faster when your code works right, you know. So don't. That's not like me flexing on you. It's just letting you know it's not really that long a program. You might have trouble getting it to work, but it's not that long a program. That's what I'm trying to say. So we're going to be reading from R0 plus R4. Yeah, I wouldn't do that. I wouldn't read from R0 at all. I'd move R0 into R6 or R7, whatever, and just read from that plus whatever the offset is. So if you want to read from R array 2, then put R into like R6 or something like that, and R4 would have 2, and then this would load whatever byte is at, the string's index 2. Load byte 0 R4. Yeah, I wouldn't do R0. If I call the function return true to R0 location when that effect R0, yeah, it'll overwrite it. Don't leave anything you want permanently in R0. Yeah, copy R0 into another register, move it back when it's done. Yep. See, function parameters only take R0. So the function parameters you pass to a function are R0 through R3. The return value is in R0. That's the standard. There's something called the ARM procedure called standard APcs, which is, there might be another letter in the acronym somewhere, that is a document fixed by ARM that says this is how you call a function and this is how you pass a value back from a function. Okay. And so this is the standard. Now, if you're calling your own functions, you can pass whatever you want. There's nothing magical about R0 through R3. They're just registers, right? You can pass a parameter in R14 if you want, but I wouldn't. Just follow the procedure call standards as much as possible. You can pass in R1, R2, R3 because they're input sources too, right? But R0 returns the value. So the first parameter to a function is R0. So if you're passing a function that takes one parameter, like is upper, is alpha, something like that, you pass it in R0, and then it will return into R0 true or false. It doesn't. You don't ever return to R1, R2, R3. It only returns to R0. The functions that we're talking about are is upper, is lower, 2 upper, 2 lower. And so what you do with these functions is, like, if you want to know if a character is an upper or an alpha or something like that, what you write is you do the LDRB, you load 1 byte from the string, and then you would do something like, I would copy that into a different register, because remember, R0 to R3 get wiped basically every time. So if I loaded into like register 8 or whatever, I'd copy from register 8 into register 0, call the function, and then check the return value in R0. If R0 is 1, it's an alpha, So we would do something like this. We'd do like a LDRB, load into, I don't know, register 8 from register 4, comma register 5. Register 4 would be your string pointer. Register 5 would be your counter, like how far into the string you are, the index, the iterator, whatever you want to call it. And so that will load this current letter. Let's say it's E, and then if you want to find out if that's a letter or not, an alpha, A through Z, then I would move into R0, R8, and you're going to be moving into R0 a lot. So basically, R0 is the hot zone, and it's going to be constantly changing and getting overridden by function calls. So what you do is you keep your actual variables up in R4 through R11, and you copy into R0, you do a function call. So the character is in R8, I copy it into R0, and then we will do the branch with link to is alpha, like that. And then we can say like compare the result to 0 and compare the result to the 0. And if the result is 0, do something. If not, do something else. Okay. So that's kind of how you're going to be doing function calls. So you put something in R0, you do the function call, and then you check the result in R0. R0 gets destroyed. I'm confused. I don't know what's going on. It's function function. Are we calling C? Does it mean call ASM function, or how does it checks? I don't know what that means. What's happening in the program is wrong server. The C++ code calls your C++ code is going to call your code, and it's going to pass a pointer to a memory address. That's the beginning of the string. And what you're going to do is you're going to iterate through that string until the character that you read is a 0. That's how strings work in C. This is a C style string. So what you do is you read one character at a time out of that string until the character you read is 0. And so when it's 0, you terminate, you return. Otherwise, what you do is you take the character and you flip a coin, and you flip a coin by calling rand. Rand, you just in assembly it would look like this. It would just be like branch with link to rand, just like that. And then when you do that, R0 is going to hold a number from 0 to rand max, which could be as low as 32,000. In reality, it's probably going to be the full 32 bits. And then you modulus it by 2. And then if the result is true, you uppercaseify the letter. If the result is false, you lowercaseify the letter. And that's it. And then you move on to the next character. So your C++ code calls assembly. Your assembly code can call C. And so you've got 3 different languages all working together in perfect harmony. The core logic of your assignment must be done in assembly, but you can call into C functions like rand. Other options would be is upper, to upper, is alpha. What else? To lower. And so to lower takes one char as a parameter in R0 and it lowercaseifies it. And it returns it back into R0. And then once it's been lowercased, you can do the strb command to store it back into the string, and then just move on to the next character. That's basically the homework assignment. And if you need to write your own C program to like print integers so you can see what's going on, you're more than welcome to do that. But you must actually do the core logic in assembly. I want you guys to get the experience doing LDRB, STRB. I would have a very hard time mixing C, CPP, and assembly together. Yeah, that's kind of the purpose of this assignment, right? So you're going to write an assembly program that gets called from C++, and then your assembly program is going to call C. But it's as simple as BL space rand, then boom. And then R0 now has a random number in it. Okay. Yeah. Sure. Okay. All right. So that is the homework assignment. What is that drink? Coffee? Yeah. Shield potion. You can copy R0 like move R0 into R4. Yes. Okay. Still kind of a flex. A little bit, yeah. I mean, it was nice that it didn't even work right the first time. I typed in LDR instead of LDRB. So if you type in LDR instead of LDRB and you try loading from a address that is not a multiple of 4, it will crash. And so I segfaulted. I was like, oh, that's not good. And fortunately, I was like, oh, I typed LDR instead of LDRB. LDRB loads 1 byte, and you can pass in any number 1, 2, 3, 4, 5. That's fine. If you do LDR, it loads 32 bits or 4 bytes at a time, and it has to be on a 4-byte boundary. It's got to be a multiple of 4. And so because I was going 1 byte at a time, loading 1 byte at a time, when I did or trying to load 1 byte at a time, when I did an LDR, I tried loading from, something that was not divisible by 4, and it segfaults when you do that. Farkle's not that hard. Yeah, well, Farkle took me longer than 20 minutes. Farkle took me a good solid 3 hours of coding to do. And that's, and that was maybe even before implementing like loaded dice and things like that. And the Warhorse people, the people that wrote Kingdom Come Deliverance, I wrote to them and said, hey, my students are doing Farkle. You got any words of wisdom for them, and they were like, yeah, we hired a guy to do Farkle for us, and it ended up taking way longer than we thought it would, and it was a lot more complicated than we thought it would be, and so don't feel bad about Farkle. Granny, if you want to load my code, you're more than welcome to tear apart my code on video. I have no shame of looking dumb in the process. It's all good, dude. I don't mind looking dumb either. Charts are treated as ints, right, in assembly? 8-bit ints, yes. What is your favorite coffee shop in town? It is Cup of Joy. So I also like Yellow Mug a lot. The owner of Yellow Mug is a great guy, and I like him a lot. They've got a fog breaker from Yellow Mug that I really like. They don't have it on DoorDash though, so I don't order it. I asked him like 2 or 3 times, like, dude, put the fog breaker on DoorDash. I'll order it from you. And they also don't have many food items on DoorDash, so I've been drinking a lot of Cup of Joy recently. This is a Hallelujah. It's just one of the greatest things ever made by mankind. Do they use Cup of Joy espresso? Nice. Yeah, I like Yellow Mug. I really like the guy that runs it. Okay. Become, who is it that was volunteering to be a sacrificial lamb? Is it DeBello? Sure. Become DeBello. You guys see that, by the way? How it does file name completion on your usernames? TCSH. Normal, sane people use bash for everything, Unix-wise, and I use TC shell, which is just my own personal shortcoming. But it does. TCSH does have nice features like being able to complete based on username and things like that. I don't know if bash does. It probably does. Bash does everything. Okay, so cd into ASM fizzbuzz. Vim fizzbuzz.s. All right. 79 strokes. Oh wait, not fizzbuzz. cd into ASM SpongeBob. Oh, we need to talk about ASM if also, actually, and the worksheet. Okay, let's while we're on this subject, let's go over this. Okay, so for the assignment, source register. Okay, you copy and pasted the README file in there. Okay. So let's take a look. So he starts off correctly. .global makes this available to the symbol table as a symbol that you can call from other files. So that is cool. He pushes the register at the very bottom. He pops the registers. Cool. He moves 0 into R4. He moves nothing into R6. So yeah, there's a problem here. And the problem is this function is being passed a pointer. A pointer is just a memory address. So every spot in RAM is just an int, right? And so like if you're reading from 3229742FF365, whatever, it's just a memory address, and it's the spot in RAM where the string begins. The string is just a contiguous block of memory. Each byte in it is a different character, and at the end of it there's a 0. And so for this function, you're not passed in the size of the string. You're just passed in a memory address. And this is how C-style strings work. And so you need to do something with R0, right? So you need to, like, I don't know, move into R6 from R0, right? You need to copy the starting memory address into a register that's not going to get wiped the first time you do a function call. Okay? So if you do this, then this code will now work properly. So it's going to read from the memory address passed in from C++ at +0. It starts off at 0 here. So that's the memory address. And I always like to annotate these things with a comment saying, this is char star sure, something like that. So I just like annotating it with like, this is int I equals 0, right? And I'll call this the counter, right? I like to put a little note just mentioning like the C++ equivalent of what I'm doing. Whenever I write assembly, usually my comments are just like what this is doing in C++. if it's not immediately obvious, right? So, yeah. So then this load byte will work properly. This is going to load the first byte from the string. It's comparing to see if that byte that was loaded is 0. If it's a 0, because it's a null terminated string, right? And so if it is 0, then it jumps down to return, and return just quits, and that's good. That's good. Good. And then branch link is set to is alpha. I don't know if set works with branch and link, but basically is alpha will, okay, so is alpha takes R0 as a parameter, right? So you pass a parameter to is alpha in R0. And currently R0 is the pointer to a string. So you're passing a memory address to it. So it's going to interpret the memory address as if it's a character, which is not going to do what you expect. What you want to do here is, remember, anytime you have a function call, you move into R0 first. This is standard practice. So you're going to move from R5 into R0, copy the byte loaded into R0, so we can pass it as a parameter to is alpha. Okay. And so this is very common where you are duplicating things into R0, because R0, it's like love. You know, like love is a battlefield, right? R0, you pass things in, they die, they get wiped when they come back out. And so you're going to have your permanent variables up here in R4 through R10 really. And then R11. And then you're going to copy from them into R0, do a function call. Again, I don't know if set works with BL, honestly. Maybe it does, I don't know. So you're going to do a function call, and then the result is going to be an R0 also, right? And so I don't know if that'll actually work. Does it actually work? Let's check on that. Compiles. All right, cool. So all right, and then if it's greater than 0, it branches to coin flip. If it is 0, that means you don't have to do anything with it, right? So he's just writing it back into the string. You don't actually need to do this. And this, like, you don't, because it's the same thing, right? You just loaded that byte. Let's say it's an exclamation mark. You check to see if it's an alpha. It's not. You don't need to write it back into the string. I would just move on. Add 1 to R4 and then branch back up to the top, right? So this is that's redundant. Okay. So that's as much as I'll give you guys for now. Okay. So yeah, that's how you call a C function. The C function is going to return its result into R0. You can check the result of R0 to see if it's true or false, and then branch down and have logic and things like that. And when it's all done, it will tell you how long the C++ implementation was and how long your implementation was. Okay. And he did a makefile as well. The optimizer is turned on. That's good. So your code's faster than assembly. I mean, your assembly code's faster than C++. So that's good. I mean, it's not working right, but it's good. It's faster. Yeah, and so he did a good job making the makefile here. So a.out, the program is dependent upon main.o, spongebob.o. are object files that have compiled code that CPUs can read in them. And how do you get from the .o files to a.out? It's this line of code right here. That will do G++, linking the two things together. This will do the linking step. The linking step is anytime you have a function call, like you're branching to is alpha, it needs to see if it can find it. And you might notice, like, is alpha is not defined in either of these .o files here. So where is the linker finding it? The linker is actually finding it in the standard libraries. And so there is something called ld.conf. Locate ld.conf. Might be misremembering the name. This is not something I play with very often. ld.conf. ldconfig. ld.so.conf. Okay. There we go. Yeah. Not something I mess with very often. Oh, that's fantastic. So it's just ARM, Linux, GNU, extended EBI, hard float. Okay. Okay, and so these are the things that it links in by default. Okay. And so if you ever wonder what this garbage long name is here, this is ARM. Obviously, we're on an ARM system, not x86. We're on a Linux system. GNU is the name of the GNU project. The GNU project. GNU stands for GNU's not Unix. It's a recursive acronym. And so if you don't move anything into a register, is it 0 or is it just random stuff in memory? It's whatever was there before, man. Whatever was there before. So yeah. So GNU is the project started by my boy Richard Stallman, and basically it's a bunch of people that release free software. You know, free as in Libre. It respects your freedoms. You get source code to every GNU project. ABI, and ABI is the application binary interface. It is how functions call each other. We're going to have a lecture on that later on, but the EABI is the extended ABI, which I think the only difference is like 64-bit numbers or something like that. And then the HF stands for hard floats. And so not all ARM systems have hard floats. In other words, not all systems have a floating point coprocessor on it. And we haven't talked about that yet, but basically your processor here actually does have the ability to do division and modulus and things like that. It's just not part of the core ARM32 assembly, which I've mentioned several times now. The core ARM32 assembly, some ARM chips are very, very cheap, and so if you don't need a floating point coprocessor, why would you waste the silicon and the money on it? And so some of them have what are called soft floats, and so every time in C++ you do a division or a modulus, it will, in the textbook, remember I told you there's an 80 line of code modulus function, it will call that, and so it will emulate floating point numbers very, very slowly. But this system is a hard float system. In other words, there's hardware that does the floating point numbers. And yeah, there's libc. So user local lib, then user local lib. Interesting. C. So here is the C library, and so that's going to get linked in by default, and that's why you are able to do is upper, is lower, rand, all that kind of stuff. All that's found in the libc library, and as we saw from the ld.so.conf file, it's being linked into your program by default. So the linker knows about all of the standard C library stuff. And so if you just call rand, it'll be like, oh yeah, I've heard of that rand person, because it's linking in this library. And a library is just a collection. It's a collection of .o files. That's all a library is. A library is just a bunch of .o files packaged together into a library. So if we use nm to look at what's in the it's a .so file. I don't know about it. The what is that? Yeah, it's a symlink. it contains all these standard C library stuff, like 2 upper, 2 lower, abs, fabs, all that kind of stuff. Okay, and so that's how it is. You can call C functions without having a .o file in your local directory that has the C functions in it. Does order matter in a makefile? So here's my makefile. It looks pretty much the same as his, I think. I think this is different here. The order does not matter in terms of dependencies, except in the order it'll probably build them. So if you do these 2 dependencies in a different order, it'll probably build one of them first one way and one of them first the other way. More or less doesn't matter. Ooh, ASM if, that's not good. ASM sponge. Who am I to be kerning? Interesting. How did my code compile then? Make clean, make. Yeah, weird. Yeah, that was a goof on my part. All right, yeah. So a.out, I copied obviously the ASM if makefile into this one. I failed to search and replace properly. So this one was dependent upon ASM spongebob.o, and then ASM spongebob.o is made using ASM spongebob.s. How do we get from ASM spongebob.s to ASM spongebob.o? We do this. And how do we get from main.o to main.cc? We do this. And I just changed it to C++17, just out of habit. Optimizer's on. AS is the assembler. You technically don't need to do this if you do it with... this is an old makefile, I think. I'd actually fix these. Weird. Yeah, no, those have been fixed last night. Oh, that's very strange. Yeah, you can actually do this with G++ as well. And if you do it with G++, you would use -c to partially compile it. And G++ is actually a front end for a bunch of different tools. And so G++ will actually look at this and say, oh, you're trying to go from a .s file to a .o file, and it actually calls AS, the assembler. And so I just put this in here so that you guys can see that you can call the assembler yourself directly. But normally, if I was doing this kind of stuff, I would just invoke G++ every time, and G++ figures out, okay, am I doing the link step? Because all this code here does is call the linker, right? So G++ is like, oh, all I'm doing here is linking .o files together. Call the linker. Oh, what I'm doing here is I'm going from a assembly file to a .o file. Call the assembler. Oh, I'm going from a .cc file into a .o file. Call the compiler and stop after. It'll do, compiler and assembler, and then stop once the object file is made. Can putting G++ for assembly file increase build time? Probably. I mean, because there's some logic in there. Here, let's time it. Yep. So, make clean, time make. So that took 1.6 seconds. Okay. And then let's make this G++-C. Make clean, time. If you put time before any command in Unix, it'll time how long it takes to run. It's like a stopwatch. It's not especially scientific. That took 1.7 seconds. So, might be a 0.1 second, difference. In a very unscientific fashion here, right? The amount of noise on that is probably more significant than any difference in running time, but I usually don't bother with it. Okay. Don't accept this as an actual answer, by the way. These things fluctuate, quite wildly. So you would have to rerun that a bunch of times to see if it actually holds up. Okay. But if it does, then yeah, then you can save yourself 0.1 seconds every time you do a full or a compile on the file. And if you're doing a really big project, well, it might actually add up to a lot. It might make a big difference if you're compiling hundreds of files. Okay. It would pass in the memory address. We do an ASCII lookup and check if that int corresponds to an alpha, right? Loading a byte does not remove it. It does not remove it from memory. Basically, in RAM, you've got a giant chunk of memory, and you've got a pointer, and then you've got an I, that's your index into the string. And all that happens is the pointer gets added to I, and that's the memory address you load from. It doesn't modify RAM at all. It just makes a copy of whatever's in the string, puts it into whatever register you want, and then you can modify that, uppercase it, lowercase it, or ignore it. If you ignore it and just move on to the next letter in the string's still there, it's fine. If you uppercase it or lowercase it, then you have to use strb to write it back into the string. At that point, then you add 1 to I and move on to the next one, and you keep doing that until you read a 0 byte out of the string. So I updated the main for you guys last night, and I updated the README file last night, and I made all the input tests. So that's what I was doing at 5 o'clock in the morning. I did sleep actually, and then wake up because I had some serious video gaming I needed to do with my buddy in Japan. And then before going to bed, I made the mistake of checking my email and realizing I had a bunch of stuff to do, so I ended up just knocking out a bunch of stuff. So the timing on this one is input file 9, and input file 9 is what you're going to be using your timing on to find out if you're going to get the extra credit or not. Okay. Who needs sleep when you have coffee? Exactly. 40 ounces of coffee a day is very healthy. That's what my mom always told me. So this is a complete works of Shakespeare. Okay. So when we do this, this is going to mocking SpongeBob, the complete works of Shakespeare. And so the C++ implementation took, was it 2.5 seconds, and my implementation took 1.8 seconds in assembly. And it's not really the fastest it could be. There's some optimizations I want to make to it, but this is a decent par, all right? So if we do it a few more times, you can see 1.8 to 2.2 seconds is, no, wait, those are micro, ticks, they're clock ticks.
That can't be, because then 4 seconds would have had to pass well.
Right, it's not. It's going to be 0.26 seconds. 0.26 seconds or 0.22 seconds. Yep. It's micro, so it's divided by a million. Yeah. Okay. So, 0.29 versus 0.18. So assembly, pretty good speed up. Okay. Considering it randomly uppercases, how does it know it's connect? How does it know it's correct? That's why we enter a random seed. So the random seed controls the coin flips. So you will get the same coin flips every time. Okay. And so the main.cc, if we come in here, you can see that the first thing we read in is a random seed using the read library, which again is superior to the normal way of seeing stuff, because you can make a variable, and in fact, you can make this guy const. You can't do normally with cn, right? Constant seed equals read. Okay, and then it copies the strings into 2 different copies. This is what I added last night. So I didn't want it to print the results if the input's bigger than 1,000 characters. So, because just printing all the Shakespeare to the screen would just be super verbose, and the input tester would be unbearable. So basically, if a file is smaller than 1,000 characters, it'll print it to the screen. If it's not, then it will only print if your code is correct or not, right? So, you sent your read lib to the C++ team. Did you ever hear anything back on that? Nope, not a single person responded to it. So it's a very I'm still on the forum, and it's very active, but the people nerd out over like changes to the language itself more than anything else. Like they've been debating recently if you can do a call point disabling of deprecation warnings or something like that. So like if you have a function that's deprecated, like let's say clock was deprecated, in C++ you can do attributes now like this, deprecated, like that. And then if anybody calls your function, then you get a compiler warning saying you should not be using this function anymore. Don't use stir copy, use stern copy, right? We talked about that last time. And stir copy. Stir copy is very dangerous. And stern copy is better, it's still dangerous. Beware of buffer over. Yeah, see, it's like in the man page now. Bugs. Anything might happen. Overflowing fixed length string buffers is a favorite cracker technique for taking complete control of the machine. Anytime a program reads or copies data into a buffer, program first needs to check there's enough space. This may be unnecessary. If you can show that overflow is impossible, be careful. Programs can get changed over time in ways that make the impossible possible. Yeah, so anyway. Yeah, so stir copy, you could put like a deprecated tag on it. So every time somebody calls a function, it would print a compiler warning. This is deprecated. You should not be using this function anymore. You should be using stir and copy instead. And so what they're debating right now is like, can you do a call site disabling of, you know, like something like this, like no deprecated, right? So yes, I understand it's deprecated, but my code here is actually guaranteed to not overflow because I've made enough room. And so just be like, yo, I know it's deprecated, but like turn it off. And so that's the kind of thing they spend all their time debating, as far as I can tell. You know, fairly sensible, straightforward things like this. Not a single response. And, you know, I would imagine they would take issue with my use of the word read, because read is a system call. And if you do man read, you'll see it's a system call. And maybe they wouldn't like overloading the system call. I don't know. But, yeah. When they want to add helpful features like that, yeah, I don't know. I mean, it's a topic that I talked about with various people at CPPCon, which is that the language itself, like especially if you look at the last couple iterations of C++, 14, 17, and 20, like there's very few features in there for like new programmers, right? There's not a whole lot in the most, you know, the past 10 years that has made your life easier as a programmer, as a new programmer. C++ 11 massively made the language a lot easier. Range-based for loops, things like that, were added in 11 and made your life a lot easier. There's a few things like structured bindings and modules and concepts. Whenever those finally kind of start coming out, will be nice. But basically, a lot of the changes are made for people who are making like header files and libraries and things like that to make their life easier as a header file writer. Locate IO stream H. And so header file people, these are macros here. Header file people are like their own, they're like their own club, you know, and they have there's all these parts of the language that are really only used by people who are making libraries and stuff like that. Maybe not only, but you know, the features were added for them. And you know, for me, it's like the main things that I would change in C++ are these: make random numbers better, because random numbers suck right now. And I think that is actually changing. There's a proposal right now to finally have some sort of sane, easy to make random number generator, which is ridiculous there isn't one. There is the random library, locate random.h. One of these is going to be it. Yeah, so this is the kind of stuff that C++ has been working on, like enable if, where you can put constraints on templates and things like that. Anyhow, so the C++ random number generator library, random.h, is garbage. I mean, it's good, from a technical sense, from a design sense, from a new user standpoint, I have never met a new programmer that could code using random.h without having cppreference.com open and copying and pasting code out of it, right? Like it's the nice thing about the C random library is that like you can just be like, how do you get a random number? Branch with link to rand. That's it. That'll give you a random number, right? And if you want to seed the random number, you make it called srand. That's it. New programmers can memorize that immediately, almost, right? That seeds the random number generator. That gives you a random number, easy, right? Whereas in C++, and my point here is that like they don't seem to be considering that as a factor, right? Or maybe they consider it as a factor, but it's not important to them one way or the other. The result is you get code that new programmers can't memorize, they can't understand, and so they just have to copy paste code. Like look at that MT19937, which is the recommended thing in a lot of so let's see, let's find some example code in here. So here's how you make a random number using the random lib. You first make a random device, and then you make an MT19937, passing in the random device to it. Then you make a uniform int distribution, and then telling it what range you want to have. And then to get a random number, you use this variable as if it was a function, passing in this variable, and then it will generate a random number for you. I've never met a new programmer that could recreate this from memory. Okay, like just this name alone, MT19937, is just like, is that the enterprise? You know, in CC. Zach says what? So when you refer to code for new programmers, you're referring to more Pythonic code? No, I mean like new programmers program in C++, but we sort of forget about that as a community, right? Like, because there's this myth that C++ is hard to use, and it's like, okay, yeah, if you design, if this is what it takes to 4 different lines of code to get a random number, right? And none of these lines of code, like new programmers can memorize. Yeah, okay, sure, it's going to be hard for new people, right? But it doesn't need to be, right? And I believe we're actually finally going to get something better in 23. Yeah, and so for new programmers, I still teach them the old C way. The C way is bad, by the way, from a technical standpoint. The types of random numbers you get are not nearly as good as the ones you get from the new library. The new library makes much better random numbers. The rand is not good at making random numbers, but for like programs like what we're doing here, it's good. All right, it's perfectly fine. Right. So here you go. That's how you make a random number in Python. Right. You want to make a random integer? There you go. Like one call, and it'll give you a random number. Right? Give me a random integer. Cool. That's it. Give me a random integer from 1 to 30. That's it. You know. And so I believe we're getting something similar to that in 23. Maybe in 20. I haven't checked. All right. What's good and bad about random numbers? Is one more random than the other? Yes. Actually, great question. So yeah. If you are making an online casino, like a craps game, you know, which is a random dice roller, if people can guess in advance what dice you're going to roll, then that's a bad random number generator. You know what I mean? Because they'll be like, oh, well, the next number is going to be a 12. I'm going to go all in on a hard 12. 12 boxcars. You know. So rand is not... it's not random, right? I mean, none of it's actually random. It's all deterministic. It's all pseudo-random. But the kinds of random numbers you get out of RAM are not of high quality. And if you do things like modulus it by 10 and things like that, like there people have done all sorts of analyses on it, and like the lower bits aren't as random as the upper bits, or vice versa. I don't remember which. And patterns crop up in the random numbers generated and stuff like that. So it is not, yeah, rand is not good from a technical standpoint, but for SpongeBob, like, who cares if you could predict what letters are being capitalized, because we want it to be predicted, because we're seeding it a certain way, and I just want kind of randomish coin flips. And so in this instance, the C random library is superior because you guys can call rand, BL rand. That's it. You want a random number from assembly? There you go. And there's no like M key, whatever, you have to memorize. That's my rant on that. Rand takes from all ints. Actually, that's not even true either. I mean, you're right, but it's technically not true. So rand here returns a number from 0 to 1 less than rand max, or no, to rand max. Okay, and rand max is a minimum of 32,000 or so, 32,767. Okay, so that's not a whole lot of random numbers, right? 0 to 32,767 is not a lot of random numbers, right? It's not a very good range. So in reality, it can give you more bits of randomness than that. So in reality, it on our system, I think it gives you the full 32 bits of random numbers, but it's not guaranteed to. It can be as small as 0 to 32,000, right? Okay. So I don't get how types confuse people. I feel like if there weren't types, I'd be even more confused. Yeah, and that's the problem with Python, right? Is that it's like, it's great, not having types is great. It saves you a word, you don't need to type string. You just be like, Bob equals hello world, print Bob. But when you have a function and there's no types on it, then it's like, all right, what am I expecting? What constraints are there on this? And in Python, the constraints are done by just using the variable. And if you use the variable in such a way that it doesn't work with whatever type is passed in, then the Python language will complain about it. But yeah, I mean, basically, large Python projects start feeling the need for types, and so there's things like Cython and things like that that will allow you to to add types to Python. Like why 32,000? It's a power of 2. Right? 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, 20, 48, 41, 96, 82, 92, 16,000 and change, 32,000 and change. Okay. So, okay. So that was my rant about C++. And yeah, I wish to do more quality of life stuff. Like, make it easy for a new programmer to get a random number, right? Because the whole point to me of a standard library is if there's a task that millions of people are doing a day, make it easy to do, right? Just make it easy to do. Make it fast, maybe, make it safe, sure. But like, common tasks should be in the standard library. If you have to roll a random number, you should have code in there that will allow people to roll a random number easily without having to copy paste code every time. All right, so let's look at ASM if, and there's something I want to show you guys about that. ASM if reference. I'm going to show you my solution to ASM if and main.c. And so here is the code. It's 3 lines of code to do ASM if. Okay. So add and set a plus b into R0. If the result is not equal to 0, then we add C and D and save that into here because it's an OR, right? It's an OR. And so what I did was I first did this part here, where I added them together the adding together. Yeah, I think all this is redundant. For those of you that took 26 with me, you know that I'm really big on simplifying if statements. We spent a lot of time on using the powers of Carnot maps and things like that to simplify if statements. And so basically, I think it simplifies. I haven't done it recently, but I believe it simplifies down to this. And so basically, I add A and B together, and if it's false, the result's 0. Then the result's going to be 0 overall, and it won't do this line, and it won't do this line. And so if you add A and B and the result's 0, then it just returns 0. If you add C and if it is true, then I add C and D together, this part here. I add C and D together and save the result into R0. And then if that is 0, then it will not do the move. But if it is true also, then it will move 1 into R0. And there you go. So it's literally 3 lines of assembly. And then the BXLR to get back out. So that's why I was able to do it in 40 milliseconds. But as it turns out, the reason why it was 40 milliseconds instead of 60 milliseconds, which is still pretty good, was because I wrote it here in main.c, and you guys are not allowed to modify main.c. And so when I pulled this out into a separate file, then the cost rose from 40 to 60. The reason being, the optimizer can work with this. And the reason why I wrote it this way is because this is what's called embedded assembly. And this is normally how C++ people do their assembly. They will embed the assembly into their C++ code. And you can actually just do this in the middle of a function, right? Like I have here. And or they just make a separate function and the whole function is assembly. Either way, you put it into your .c or your .c code, and the optimizer can work with it. So the optimizer will look like that. Will look at this and be like, okay, that's 4 lines of code. Add da 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 da. Okay, cool. I'm going to inline that, and then the optimizer can strip the overhead of the function call out and actually embed this into the call site down here. No, not there. Here. So when it calls that function, it will actually not do the branch with link. It won't do the pushes. It won't do the pops. It'll actually take those 3 lines of assembly and put it right here. You don't even have to return, right? And so that's 3 lines of assembly versus having the branch with link, push, 3 lines of assembly, pop, right? So rather than 8 things, it's 3. And that's why the running time dropped from 60 to 40 milliseconds by putting it in here. It's because when you put it in here, the C++ optimizer actually can work with assembly code. And it will actually be like, oh, thank you, bloop. And it'll just take these 3 lines of assembly here and just put them down here at the call site like this. And the code goes a lot faster. Okay, so that's why people typically will do it this way. If you have it in a separate file, that limits the amount of optimization you can do. If you have it in a separate file, the optimizer, there is something called link time optimization that is kind of coming on strong now, but normally the optimizer works within 1 file at a time. It's called a code translation unit, in other words, a file. But it's not a file because you have, you know, these things, because it includes multiple things into it. But in 1 file, the optimizer will work on it and do things like inlining and things like that. So if you want something to be inlined, I put the keyword here, inline, which I don't think will matter. See what would happen if I take it out. Ooh, 98 milliseconds. 40. Okay, there we go to 40. Okay, yeah. I don't think it'll matter.
Can you go over like the process of actually like
that's what I'm going to go over. So yeah, I don't think the inline keyword here actually does anything because the code's so short, the optimizer would inline it anyway. So you know, I put it in there because I kind of want it for you guys, you know, so you can see that keyword. And there's also this register keyword here, which I think also won't do anything. You can actually, when you do this, you can actually reserve a specific register for this variable, So you can actually be like register int res equal, and I think you actually like put in like R0, something like that. Yeah, I don't know. Yeah, there's a way you can actually reserve a specific register for a variable for optimization purposes, but it's not necessary here because the compiler, I mean the register keyword itself isn't. It doesn't do anything, right? But I also put that in there to see that this is actually a keyword in C++, and if you need to make sure that res is R7 or something, you can do that. But the optimizer will figure it out anyway because I'm returning it, so it'll be in R0, right? So the compiler will figure that out without you. So, yes, this is how you do something called embedded assembly. Okay, and this is very common. If you look at a lot of high performance code, video games and things like that, when they need the absolute pinnacle of speed, they'll do this, or they'll try it and see if it's faster, right? Because sometimes you need speed, right? As fast as CPUs are, we always need more speed. And so the first 3 semesters of computer science, I tell you guys not to worry about speed. Worry about correctness. Don't use square brackets with vectors. Use .at. Don't use arrays. Use vectors. And then when you compile your code, it compiles it with like 5 levels of safety on it. It compiles it with address sanitizer and undefined behavior sanitizer and the safe C++ library and the debug options turned on and all warnings turned on and et cetera, et cetera. So I have turned on multiple layers of protection because it's important for programmers to get correctness down first. There's absolutely no point having your code run incorrectly quickly. My code crashes twice as fast as your code crashes. Right? So, there's absolutely no point crashing more quickly than someone else, right? So, I try to instill in you guys correctness as the first and main priority. But then, and the other reason for that is a lot of times when your code is correct and you run it, it's like, oh, that was fast enough, right? It's fine. A lot of people worry about speed unnecessarily, right? Because a lot of times you run your code and your function runs once every 10 seconds, and maybe it takes an extra 10 milliseconds. Once every 10 seconds, who cares? But if your code is being run a lot, then take CSI 45. So what we have here is a way of embedding assembly inside of C++. Okay, and this is how a lot of professional programmers do it, because again, if it's in the code, then the optimizer can work with it. All right, so this is a function. It's a C++ function named inline if. It takes the 4 parameters. It's exactly the same as I don't need this here, do I? Yeah, I don't. I actually had it in a different file. So I actually had it in a different file because I wanted to see if the optimizer, if it could work with it, and it can't. So if it's in a separate file like this, the running time rises 50%, right? So I put it in here instead. But basically it just works the same way as calling your, as any function, right? And so this is what allows you to embed assembly into C++. And what makes it tricky is that you need to tell C++ what registers or which variables, right? You have to say okay, all right. So we've got this variable here named A. I want that to be register 5, so to speak. And we got this guy, and that guy is going to be register 6. And so in your code, you have to link, there's a really weird syntax here. And the weird syntax is this stuff. And that stuff is saying, how do you link the variables in C++ to the variables in assembly? So there's a couple lines of glue here that say, okay, that one's register 5, that one's register 6, that one's register 7. And you see I'm just passing in the variable names here. Res is the result, right? So that means you're going to write to it. You can read and write to it, I think. This means you can read from it, but you can't write to it. So I'm reading from A, B, C, and D. I'm not writing to them, right? And I am writing to the R0, this guy. Okay. So this weird syntax here is linking. That's the connection. That's how you connect R5 to a variable named number of bananas to buy, right? And so you use a square bracket. You give it the name of the variable in assembly. So you don't have to use R5. You can if you want, but you can give it a name. Look, there's variable names in assembly. Yay. Cool. So what's in the square bracket there, which is optional, you can give the variable name in assembly. Cool. So I'm just calling it input A. I just came up with that name. You don't have to call it that. You can call it Bob or banana or apple, whatever. And I'm saying I'm reading from it only. I'm not writing to it. I'm reading from it from the variable named A. Okay. And then make a variable named input B for assembly. Also read only from this variable here. Do you guys understand? Does that make sense? You're not going to remember this syntax, so just copy and paste it. There's an example in your ASM demos on how to do this. But does that kind of conceptually make sense to you, that you have to connect, result, I just made that name up, result. And so this code here connects the variable named res with, in assembly, the variable named result. So that's the bridge between them. If you just use like R0 and R7, you have absolutely no idea. You know what I mean? Like, if you don't do that, like, how do you know what registers, what variables are going to be? Like, is this guy going to be register 7? Is he going to be register 8? I don't know. Maybe the optimizer is going to remove him entirely. I don't know. You just be guessing register names and hoping the optimizer just picks the same registers for your variables. No, that's you can't do that, right? So you have to link the assembly and the C++ together so that they're working on the same page, so that they are using the same registers for the variables in assembly and the same registers for the variables in C++. Is it slower than using registers? These are registers. This is assembly, right? Add and set. That's going to be R0. And so when you have the percentage result there, that's actually R0, because the C++ code knows that that's the return value. So it will, when this code gets run, it will substitute in R0 here. It'll substitute in, or maybe not, because A is R0, maybe, I don't know. So I don't need to worry about it. The C++ compiler will figure out what registers all these guys go in for me. Okay. It is not slower than using registers, because it is using registers. This is assembly. Look, it's just assembly. Okay. And rather than using R5, R6, R7, I get to use variable names. Yay. It's pretty cool. The new line and the tab are optional. You don't actually need to do that. It's just there. Well, maybe the new line is required. But if you were to compile this code, and okay. So this is the actual assembly that it generates here. Okay. These are comments. But they're comments emitted by the compiler to let you know, information about the function. So that's moving the stack pointer down. Stack pointer loading from the stack pointer. Is this? Oh, I didn't. Yeah. Let's turn the optimizer on. Okay. So this is a little bit better. So, and this is saying we are on line 12 of main.c, I think. Okay. So when it emits the assembly code, you want to have the new line in tabs, because it makes your assembly here look nice, because otherwise it'll be not not tabbed over, I think. And you can see that the spaces that I put in here came into the assembly. So all it does when you have those assembly statements is that it just literally copies and pastes them right into the assembly of your C++ code. The only magic that takes place is what register is who. That's A, that's B, that's C, that's D, and that's result. So it actually is smart enough to assign both A and result to R0 because it's reading from A, it's not writing to it. So it knows that, you know, it's not going to be read from after that point. So it reads from A and it writes to result. It reads from C and D, writes to result, and then it move NE. So it's putting a 1 into R0 if the result's not equal to 0. And what's interesting about it is that there's not even, you see how there's no push, there's no pop, there's not even a return from the function, right? And the reason why there's not a return from the function is because it's inlined, right? This code will not ever actually get called. This code will not actually get called. This is a inlined function. So what will happen is if we look at move NE, you can see down here, there it is. In the middle of main, it just bloop, it just put those 3 lines of assembly right there, including the weird formatting that I have here, right? It just so yeah, it just literally copies these 3 lines into the assembly. The only tricky thing about it is this, right, where you just have to tell it how to connect the registers in assembly and the variable names in C++. That's the only catch to it. Okay. Any questions, guys? This is actually how it's done, right, in real life because of the optimization benefits you can get out of it. So if you look at the source code for various video games, even to this day, League of Legends uses assembly in its particle effects code. You know, they rewrote their particle effects code over and over again in C++, couldn't get it fast enough, so they switched to assembly and wrote it over and over again in assembly and ended up drastically raising their frame rate as a result. And so, you know, as you can see, the code that you get out of this can actually be really fast. Any questions? Any questions? You guys still here? Okay. So, kind of cool. What do you guys think? Okay. All right. So for ASM, if was De Morgan's law applicable? I don't see a not on there anywhere. Maybe. I don't know. Yeah, all the rules of Boolean logic you could apply to simplify it down. What I did when I solved it was I made a Carnot map and used the Carnot map to simplify it. And then I looked at it and I made sure that there was a situation like this because I knew what kind of trick I wanted to write for my assembly. And so I made sure that this could be done, you know, using very few lines of assembly. I wanted to make a fairly high skill cap, you know what I mean? So that as you guys worked on it and worked on it and worked on it, you can get the assembly code down very, very small. The Kearney map, that's right. BL for ARM to use CPP, ASM for CPP to use ARM. BL for ARM to use CPP, ASM for CPP to use ARM. Yeah, the one caveat with that is name mangling. So let's talk about that real fast. So cd asm SpongeBob dot reference. So let's say that I have a function here in C++. Let's call it void print int, taking an int x, and all it's going to do is cout x. Okay, so you could do this if you wanted. You can't modify main. You'd have to make your own .cc file if you wanted, but I'm not going to, just for the sake of simplicity here. So here's printInt. Okay, you guys all understand this? It takes an integer, it prints it. Boom. Cool. You guys understand? Now, I'm not going to show you my assembly code, but let me just make a new one called I don't know, bob.s, and bob.s could call printInt, right? And so I could like move, I don't know, 42 into R0, call printInt, global bob, and that's right. And then we'll push LR and
Is this your game
pop.
game class?
This is not my, it's not my game class, yeah. So that should work, I think. Right, 4 lines, thank you. Okay, so you guys understand? So if you call Bob, it should print the number 42 to the screen, right? You guys understand? Wrong. This code will not compile. This code will not compile. And the reason why it won't compile, it looks like it should compile.
Why are they saying a bunch of yes?
I'm asking them if they understand, and I like because sometimes silence from students means they understand, and they're bored, or like they're like, yeah, I get it. And sometimes silence means they are baffled beyond human comprehension and don't want to admit it. And so when I ask them, do you understand? The students that understand say yes, and the ones that are baffled beyond comprehension stay silent. But it makes me feel better about myself as a professor because at least 4 people understand, right? And if these 4 people can understand, clearly all of them understand. That's just how it works. So this doesn't work. And the reason why this doesn't work is because if we g++ -c main.cc, if you look at what using nm again tells you which functions are in a program. If you look at what's inside of main.o, these are all the functions. U means it's undefined. It's calling these functions, but it's not in here. These are all standard library functions. But if we search for printInt, pipe through grep printInt, there it is. The name of the function is actually _z9 print_int I. So that is actually the name of the function. So if and see how it's T, that means it's in the text segment. So that the text segment's your code, right? So if I want to call this function from assembly, from Bob, I would actually need to do this instead. Okay. Now it'll work. All right. So g++ main.c bob.s ASM SpongeBob error it's main.cc, sorry. And it compiles fine. But if I had done it the other way, like that, and tried compiling it, I would get a linker error. And the linker error is because there is no function named printInt. C++ does something called name mangling. Name mangling. And this was this is how C++ allows you to have, and so this function doesn't exist. That's why I've been having you guys do C with assembly. C does not do name mangling. Whatever function name you have in C is the name you would call it from in assembly. And whatever function you have in assembly is how you'd call it from C. C and assembly go together very nicely. C++ does something called name mangling, and it's not pretty, right? It's not pretty to look at. Okay. So why do the other functions you work with have a simple function called with BL? Because extern C will do, if you put this in here, extern C disables name mangling. Okay. And so name mangling is what allows you to have 2 functions with and so if I did this, let me just go back into Bob. Okay. So now the code will compile. This code will compile because I disabled name mangling by putting it within extern C. Extern C basically says turn off name mangling. And that's what allows C++ to interoperate with C and assembly and things like that by disabling it. Does it purely transition into C code, or is it C-like within CPP? It's still C++. It's still C++. Like, that was C out, right? Like, you know, this is not valid C. You know, C uses printf and scanf. C++ uses C in and C out. But what happens is, all it does is it turns off name mangling on the function call itself. So the name of this function would be printInt instead of underscore z whatever, you know, print it. Yeah. And so you can actually put your C++ code into here and then have C and assembly functions call it. So this would actually work very nicely. Now you're like, why wouldn't you just put everything in there? Well, let me show you. The this is why name mangling exists. C++ allows what's called function overloading. So C++ function overloading, which means two functions with the same name. Technically, this is illegal. You cannot actually have two functions with the same name. As you've seen in assembly, if you branch with link to print int, which one do we call? You know, there is one name, you know, for it jumps to it. You cannot actually have two different functions with the same name. And so Bjarne's brilliant strategy was g++ dash c, yeah, sure, c main.cc name main.o main pipe through grep print int. Is you will see it when you name mangle it, there's one version of printInt. You see the last letter there? There's one version of printInt that takes an int, and there's one version of printInt that takes a short. See? Yeah. So what it does is it bakes the parameter list into the name of the function itself, and yeah. And if you notice, the return type is not in here, right? I changed it so it's returning an int instead of a void. That actually doesn't mean return void. Okay. The reason for that is because you can't actually overload on return type. Like you cannot have one function that returns an int and one function that returns a void and otherwise be the same. This will not compile. Functions cannot be overloaded on what they return. They can only be overloaded on their parameter list. So if we compile this, it'll be like ambiguating. That's a great word, ambiguating. Ambiguating new declaration of int print int. Old declaration is here. Okay, so can't do that. If you wanted to have a char, or if you wanted to have a long, let's put this back. Void. nm main.o. You can see the char version has a C, the long version has an L. You guys with me on this? So, long. So that's an X. You don't really need to know this. It's just kind of a curiosity. Because C++ hides it, right? C++ hides what it's doing. It's hiding the name mangling behind the scenes. Okay. But that's why assembly can't call C++ by default. If you just call printInt, right? If your assembly code were to just call printInt, which one? It's ambiguous, right? And so this is Bjarne's big advance from C, is that it allows you to have two functions with the same name. Because in C, it's really annoying. In C, you have to have like abs, and then you have to have fabs, right? Abs takes an int, fabs takes a float, or a double, right? And so in C, every version of a function that takes a different type has to have a different function name. And it's super lame. It's super lame and annoying. So, man fabs, right? So you have fabs, and you have fabs for float, fabs, flabs, Flabble. Fabs is great. It's fabulous. But then you start getting into flabs. You know, you want fabs. You don't want flabs. You know what I mean? It's session 3, I think. Yeah. And then there's abs, and then of course you got your laboratory retriever named labs, and then you've got labs. You see that? You see how annoying that is to write? In C++, you just call abs. You just pass in an int or a char or a float or a double or a long. It doesn't matter. It's all abs. It all works. And in C, it's like it's flabble, you know, labs. You guys understand? It was a nice advance, but it does make interoperating a little bit harder. And one more note on this before we move on to caching is what if I were to put these guys into mark x, mx, d, single quote x, right there. Would this work? This disables name mingling. This disables name mingling. So we're going to have two functions named print int now. I've read a couple C books, and honestly, despite it being a little more tedious and weird, I like it more than C++. There's nothing wrong with C. There's nothing wrong with C except for strings. Strings in C are 100% garbage. Okay, so if I try compiling main.cc now, conflicting declaration. You see that? You can no longer overload. You can no longer overload because D7D, okay. Left shift 7, because with name mingling disabled, then you can't have two functions with the same name. Okay. So, all right. What do you mean by short? It's a 16-bit integer usually. Doesn't have to be, but nowadays a short is a 16-bit, more or less across the board. A int is 32 bits, a long is 32 bits, and a long is 64 bits. Doesn't have to be. The standard actually gives you a range of values that it could be, but that's kind of typical these days. What about a short? You mean a char? Yeah, I actually don't like using words like short and long and things like that. I prefer just being like, I want an unsigned int 64p, right? Something like that. Like if it matters, I want a unsigned 16-bit. I want a signed 16-bit. I just specify it. Like I don't use short, right? I use give me a 16-bit signed integer. Because if it matters, it matters. If it doesn't matter, just use an int. I don't know, right? Int is going to be whatever your register size is. But if it matters, like if you need it to be 16 bits, a short, use 16 bits because you don't want to move your code to another platform that has 32-bit shorts and be horribly surprised by the results when your code doesn't work. Just specify directly. In general, I'd say that's good practice across the board. Can you write short? I don't think so. What about a short long? Does that work? No. Can't do that. Short. We like shorts. No. Can't do it. What about a long? Does that work? Long is too long. I've never seen that error message before. That's amazing. Long is too long. It's too long. It's just too long. GCC can't handle it. Maybe another compiler can handle it, but it's too long for us. I'm sorry. It's funny. I want an unsigned 100. What is it? Try a 128-bit. No. Yeah. So I kind of wish they would add in basic types that were longer than 64 bits because I actually do need them sometimes. But okay. So Any questions about this? We're going to go back to caching because I found mistakes on more or less everybody's caching worksheets. You said you use suffixes at the end of stir b, but every time you try it, no, I don't think you can use suffixes with load or store. That was a mistake that I made last time. I posted that on Discord after the lecture was over. You cannot use suffixes with load or store. Yeah. So just load or store, and then do a comparison with 0 or whatever. Okay. Long, long, short, long. Any other questions? Any other questions? Yeah, the homework assignment itself should be pretty easy. You can use calls to toUpper, which uppercase is a letter, toLower, which lowercase is alpha, to see if it's a through Z. You can use those C functions, it's fine. Just have the core logic all be in assembly. Are we going to go over the cache worksheet? Yeah, right now. I just want to make sure there's no questions about this before we move on. Did anyone do the caching worksheet right? Yeah. Not many. Not many. I felt good about it, but who knows? I think yours is correct. I think yours is correct, if I remember it. Okay, but what I'm going to do is I'm going to go over it in more detail, and I'm going to let you guys resubmit. Okay. So, mind giving us a list of what? People that got it right? Did yours work? No, Amuya, yours had errors in it too. So let's see here. Chamois. Yeah, let's do this. Source of energy is food. Okay. Adobe Acrobat is not responding. Well. Okay. I didn't know that a single PDF would be so taxing on my Core i9 processor. All right. All right, so let's go through this.
Wait, was it potentially because you were only counting since the last load instead of cumulative?
No, I like I told you guys, I'm smart enough to handle that. It was this part here that you got wrong. Okay, so let's... One note. We're talking about ethics in CSI 1 yesterday. CSI 45, let's make a new page and name this one 2, 4. Okay. So let's draw. The cache. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, too many. Okay, so this is a 10 entry cache, and this is direct mapped caching. So that means that if anybody goes into a slot and somebody else goes into the slot, it knocks them out. One-way set associative is the same thing as direct mapped. In reality, these things will be like 8-way. So each of these buckets will actually be like having enough room for like. There's actually, in reality, they do what's called 8-way or 3-way or 4-way set associative. But like if it's 8-way set associative, that means there's actually 8 different people that can hash to the same spot. And once the 9th person comes in, then whoever was least recently used or least frequently used, depending on the cache policy, that one would get evicted and the new person would go in. So for this assignment, like I said, we are using a very simplified, super oversimplified version of caching, but it will get the concepts to you guys. Okay, so let's look at program 3. Let's look at program 3. All right, so we're going to load 1. And so I'm actually just going to write down who's in L2, L3, and stuff like that. They're all in RAM. Okay, so 7th gen currently went over this. All right, load for memory address 1. So memory address 1 modulus 10 is 1. And so we're going to have 1 in here. So we are going to have 1 in slot 1. And so L2 cache has 1 in it. L3 cache has 1 in it. Okay, that's first line. Second line. And so that was a cache miss because we're loading from RAM, so that's 200 cycles. The next is a cache miss. Again, all of these are going to be cache misses because the first time you load something, it's going to cache miss. You're going to get a cold start cache miss if you ever load something without reading it. So without writing it, sorry. So we're going to get 4 cold start misses. It's going to be 800. But what is the state of the cache after we do these things? So LDR11 11 modulus 10 goes into slot 1. And so slot 1 now holds 11 instead of 1. L2 has both 1 and 11 in it. L3 has both 1 and 11 in it because L2 is size 100, right? So L2 is of size 100 and L3 is of size 1000. And the reason why I'm choosing these cache sizes is so that the modulus is easy for you guys. In reality, these caches are, like an L1 cache is going to be like 16,000 or something like that, right? And so after we've read 11, 1 has been knocked out of L1 cache, but it's still in L2 cache, okay? So then, let me use a different ink for the third one. So load 111. So 111 is going to knock 11 out of L1 cache. And 111 modulus 100 is 11. And so that's actually going to knock this guy out of L2, but it leaves 1 in there. Okay. All right. And then all 3 of these guys are happily coexisting in L3 cache, right? So there's been a fight over slot 1 and L1. There's been a fight over slot 11 in 111, but L3 is big enough that all 3 of these guys are in it. Okay, and then we load 1111. So 1111 is going to knock 111 out of L1. Use a third color for this one. 1111. 1111 modulus 100 is 11 also, so that's going to knock this person out. 1111 is in there, and 1111 modulus 1000 is also 111, and so it's going to knock this person out here. And this is the state of the cache after we've done these 4 loads. Okay. Now, and so all 4 of these were cache misses, so Shami is correct. It is 800 cycles on the first section. Now the next section, LDR 1111, that's in cache, right? So the CPU checks L1 first. It is in L1 cache. You get a cache 1 hit. So that is 4 cycles. Boom, we're done. We then do a load 111. Okay? So when you do a load 111, the CPU will check L1 first, not in there. Checks L2 second, not in there. Checks L3 third, not in there. Okay, so that's a RAM hit. So that's 200 cost. And then the caches all update. So what's going to happen is, what color did I use? Blue. Blue. So 111 is in there. 111 is in there. And so that was a cache miss, and it has evicted 1111 out of all 3 of its spots. We then load 11. 11, Shami is wrong here. This is not a cache miss because 11 is right here. It's in L3 still. We have not touched it. So what's going to happen is the CPU, let's say the CPU is sitting up here. The CPU checks L1 first, checks L1, and then, okay, it's not an L1, so it checks L2, not an L2, so it checks L3, it's in L3. So this is called an L3 cache hit, and so the cost of that, I think, is 75 cycles, okay? And then the caches all update. So the caches, this guy gets evicted, That guy gets evicted. Oops. And we have now 11 in here. And we have, what are we, red? 11 in here. Okay. So, after this is wrong here. This should be 75. Okay. And so then LDR1 is going to be, it's also not evicted from cache. It's going to miss, it's going to cache one miss here, but it's going to cache it's going to L2 hit. It's going to get a level 2 cache hit. And so the level 2 cache hit, I believe, is 20. And so, or 10? 10. Yeah. So it's going to be 10 cycles for this one. Okay. And so then the caches all update, and we get, I keep misclicking on that. And then we have 1 in the L1 cache. The wrong font color. 1 in the L1 cache after that. Okay. And so coming down here, let's finish it off. LDR11, that's going to be an L2 cache hit. So, and then L1 cache will update. So that is correct, 10 cycles. It loads LDR11 again, that's going to be a cache hit. So that is going to be 4 cycles. LDR1 is level 2 cache hit, so 10 cycles. And after every load and every store you do, the caches all update. Whatever the last thing was that you touched, that will be an L1 cache. And then LDR11 is again an L2 cache hit, and so that's 10 cycles also, and this is how the cache finishes. So Shammy's mistake was, I think, on these two here. Okay. Somebody did this in the head. Good job. No, you can't really do it in your head. You have to sketch it out, right? You have to kind of write down this kind of stuff. So let's look at someone else's. So DeBello, let's see, 200, 200, 200, 200, cache hit, yes, cache miss, correct, hit, yes, 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 yeah, so DeBello got this one correct. Okay. So, any questions about this? You want to see which one's wrong for you? Sure. Okay. It's really important you guys develop like an intuitive understanding of how caching works. If you keep hitting the same spots in memory, one of the reasons why for ASM SpongeBob I have the C++ code go first is to give your code an advantage. Right, because the C++ code is going to iterate over that chunk of memory, and it'll all be nice, hot, and fresh in cache. And then when you get to go second, it gives your code a speed boost. So Muya's favorite source of energy is coal. All right, and if we zoom in here, okay, so we can see that. Ooh, there's a highlighter tool. Paint. There we go. We're going to draw purple paint on its code. So that is correct. No, can I not paint on this? Really? I have to use my mouse? Like a peon? What is this? What is this? Highlight? No? Whatever. Okay, so yes, that's correct. That's correct. LDR 1111 is 200. That's correct. And then here we have 75 for a L3 hit. I believe that's correct. And then this is 1082, which is 3 cycles, not 4. So, yeah. So you wrote down a 2 instead of a 3.
You got the same thing as I did when you did it on the right there.
A 2 is impossible.
For this is LDR that after the 11, 1089. I'm confused.
That's not 1089. It might just be a handwriting issue. Do you see this on the screen?
Yeah, no, I see. I did write 1089, but when I was going through it with you, I also got 1089, and I was following every edition you were getting. You got the same as me.
But that's a 2, I think.
But the one right before it would have loaded 11 into L2.
It would have loaded 11 into L2.
So you can see there even at the end you still have...
I think it might just be a handwriting issue.
No, you're reading my handwriting correctly. That does say 1089. But what I'm saying is you also got 1089 when you solved it on the right.
But that's not 1089.
Wait. Oh, wait, what do you think it's saying?
That says 1082.
Oh, no, that is a 9. Sorry, then it is a handwriting issue.
Yeah. Yeah, I'm just not seeing it. I'm sorry.
Oh, okay. Never mind then. Yeah, that is a 9. I thought you were saying it was 1089.
Yeah, I don't know. Zoom and enhance. Okay.
It does kind of look like a 2, but nothing.
How does that?
Nothing adds.
How's that a 9?
Nothing adds 3.
There's like.
So how even?
I know, right? But like, you have a line sticking up here. It's like an R, kind of.
You know what?
I don't know.
My handwriting's bad. We all know it. But there's
All right.
no way that I can annotate it.
Yeah, I know. That's why it was wrong. Thanks, Backler. Thanks. He drew the 9 over it for you. There it is. We found it. It's a question mark. Yeah. It's like the students who answer a true and false question like this, kind of, you know. It's there's my answer. Is it true or false? Yeah, it's yeah. Okay, so maybe that's all the problem there was. Anyhow, so let's do one more, I guess, because this is actually pretty important. And they do appear on the midterms and stuff like that. The midterm will be Thursday of week 6. So 2 weeks from today, we'll do our first midterm. And what have we covered? We've covered. We'll need to do some more bitwise stuff. I guess I'll post the bitwise worksheet for you guys first, and then I'll have to make up another caching worksheet for you as well to work on. Will there be a programming section? Maybe. Usually midterms next week. It's week 6. Week 6. Yeah, it's week 4 right now. So there will be assembly on the midterm. I don't know if I'll actually have like a live coding section or not. I might. That sounds like fun. Good suggestion, Cabot. Thank you. So if the people demand it, we can do live coding in assembly. Program is already 40% of the grade. Yeah. Now normally when I do it, it's just like explain to me in English what this assembly code is doing. So here's some code and it's a loop. You're like, okay, that's adding up all the numbers in a vector or something like that. It's usually just multiple choice. Okay, so let's do one more of these and work on. I erased a little too much. See if we can work on our understanding of caching a little bit. So the CPU always updates the caches, or the memory subsystem, if you want to be technical and precise. Okay, so draw. Thank you. So we're going to store. Okay. So the first guy I'll be red. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So 4, 3, 8, 4 is in slot 4. 2, 1, 2, 1 is in slot 1. 81, 20 is in slot 0. and then these guys are in L2 and L3 as well. So we got 4384, we've got 2121, and we've got 8120. And so these guys are in slots 84, 21, and 20. And in L3 we have 4384, 2120, 8120, and these guys are in slot 120, 121, and slot.
It's like 4784.
See, now he's all salty. 4389. There you go. 43. Okay. Let's fix this one too. There. Okay. So this guy's in slot 84. This guy's in slot 21. This guy's in slot 20. Okay. And now we're going to do some stuff. So load 1100. So 1100 is going to knock this guy out of slot 0, and we're going to have 1100 in there. That's slot 0, so he's not going to affect any of these guys. So this one now has 1100 in it. That's in slot 0, and this guy is in 1100. He's in slot 100. Okay, load 2121. So 2121 is still in L1 cache. It's a level 1 cache hit, 4 cycles. LDR 4384 is in L2 cache, and that's, I can't even read my own handwriting. 4384. That's really terrible. Okay, yeah, that's still an L1 cache, so that's a cache hit. 8120 has been knocked out of L1, but it is in L2, so that's an L2 cache hit, so Chamois all correct there. Store 1212, so 1212 goes in there, 1212 goes in here, it's in slot 12, 1212 goes in here, it's in slot 212. Okay. Store 3913, so that's going to go into slot 3. It's in slot 13 here. 3913, it's in slot 913 here. Store 1284. Okay, so that's going to knock you out of here. Oh, erased a little too much. So you are 1284, right? 1284 is here now. So 12. Oh, so it's going to knock. So that's slot 84. So that's going to knock him out here. 1284. So he's in slot 84. And then that's slot 284. So that guy is left alone. So we got 1284 in slot 284. So you see how this works? Like L3 cache, because it's bigger, more things can coexist peacefully. But the smaller caches, they'll get purged by other people fighting over the same slots, and that's why we have small and fast, because the L1 cache is very, very fast, and the bigger caches are slower, but they can hold more entries. And so by having a cache hierarchy, then the things that get used a lot get the absolute fastest access time. Things that you used a medium amount get a medium amount of access time. Things that get used occasionally get a longer access time, and then things that are used very infrequently are held in RAM and are slower. RAM is very slow. CPU's advanced much quicker than RAM at speed. Okay, so part of the reason for that is just cost. So DRAM is not as fast as SRAM technology. Back in the day, you were able to choose whether or not you wanted to buy SRAM or DRAM, but DRAM could make I think the price ratio was about 2-to-1 to 4-to-1, something like that. So it was kind of like, would you rather have 4 gigs of RAM or 1 gig of RAM, at the same price? But the 1 gig of RAM would be faster, you know what I mean? So like, people who wanted high performance stuff would buy SRAM, and people who wanted more capacity would buy DRAM. And as it turned out, people wanted more capacity rather than speed. And the cache hierarchy also mitigated a lot of the the benefits of SRAM, because L1 cache is SRAM. So essentially what we have today is an SRAM cache for a DRAM backend. Okay, so we're going to load 1284. Load 1284. And so that is an L1 cache it. Load 4384. Not in here, not in here. L3 cache it. 75 is correct. Load 1212. 1212 is L2. So, or L1. 1212 is in slot 2 of L1. Yeah, L1 cache it. Cool. Load 1100. 1100. That's wrong. That should be in. That should be at L1 cache it. Right? Because the last time we did anything was here. Right? And we had. Oh no, sorry. Yeah, no, that guy's. Yep, you're absolutely right. It's at L2 cache it. Sorry. That guy purged 1100. Okay. And if you guys want to do it in your head, you can just look backwards and see the last time something was used and the last time something overrode its slot, right? So you can just go backwards that way. So for this guy, 1212, you can just look at slot 2. Nope, the last time it was accessed is here. For this guy, the last time slot 4 was accessed was here, and it was not me. All right, so let's look at the last time 84 was accessed. Well, the last time it was accessed was here, not me. All right, let's look at the last time 384 was accessed. Here. So it's still in L3 cache. So that's the way you do it in your head. If you got the worksheet right, well, you have to do the new one. Got to go to work. Yeah, have fun. See you. You know, I'll just let you guys fix your worksheets. Okay. So if you guys got them wrong, just resubmit, and I'll just have you guys do it that way. Okay. So the thing should still be open. So just edit your file and copy Muya. No, actually try and work it out. Resubmit it, and then next Tuesday I will grade them for real. Okay. That way you don't have to. I don't have to waste the time of people that did it correctly, I guess. I haven't missed yet. Will you let us know if we got it right? It is going to be on the test, so yeah, I'll grade them, I guess. I don't want to grade them twice, do I? Yeah, I'll grade yours, Rivera. How about that? We'll find a compromise. All right, so that's it for today. Work on ASM SpongeBob for Tuesday. Make sure you get the Zybooks done. Redo the worksheet if you got it wrong, which was most of you. And then our late turn is accepted. Yeah, it should just work on Canvas. It'll be flagged as late, but I'm telling you that I'm accepting it late. So yeah, it's fine. Cool. So hope you guys learned a lot today. Learned about embedded assembly, which is really useful stuff. Went over caching again. How to link assembly and C++ and C together. You can take a look at your ASM SpongeBob. Sure, just hang out right after this, and I'll take a look at it. Yeah, and so yeah, good class, everyone. Thanks for coming, and I will see you guys on Tuesday. Have a great weekend.